Hello all, welcome to the new lecture of integral equations. In this lecture, we will discuss the equivalency of differential equation and the corresponding integral equation involving the Green's function. In the last lectures, we have discussed about the definition of Green's function and how to determine Green's function. Now we will show that this Green's function, the integral equation we have formed using the Green's function is equivalent to the differential equation, or the differential equation can be derived from the corresponding integral equation involving the Green's function. First of all, we have formulated the Green's function from the differential equation Ly plus phi of x equal to 0 together with the homogeneous boundary conditions given. Now we are doing the converse process. So for that, consider the integral equation y of x is equal to integral a to b g of x theta phi theta d theta, and number it as equation number 1. We show that equation 1 implies the differential equation Ly plus phi of x equal to 0, which is equation number 2, together with the prescribed boundary conditions. In the last lecture, we have formulated the Green's function as when x is less than theta, the value is minus 1 by a u of x into v of theta, and when x is greater than theta, its value is minus 1 by a v of x into u of theta, where u of x and v of x are the non-trivial solutions of the homogeneous differential equation Ly equal to 0. And the thing is that u of x satisfies the boundary condition at a, and v of x satisfies the boundary condition at b. Okay. So in order to get the differential equation, we have to find its derivative of equation number 1. So differentiating, before differentiating, we expand the integral 1 by applying this definition of the Green's function. Okay. So the Green's function, we have to split the integral. We know that the integral of the variable of integration is theta. So we split the integral from a to b as with an intermediate as x. So a to x, integral a to x plus integral x to b, and we split it in this way. And in the first integral, when a is integral a to x, g of x theta is when a is first integral is from a to x, isn't it? So in that interval, that is interval a to x, so theta lies in this interval. That means theta is less than x. Theta less than x means x is greater than theta. So when x is greater than theta, the value of the g of x theta is the function minus 1 by a v of x into u of theta. So in the integral a to x, we write the integral as integral a to x minus 1 by a v of x u of theta phi theta d theta, because equation number 1 contains phi theta. Plus, now split the integral, then the second integral will be from x to b, and in the interval x to b, when theta belongs to x to b, theta is actually greater than x, since x is the lower limit in this interval. So theta greater than x means x is less than theta. So in that interval, the value of g of x theta is minus 1 by a u of x into v of theta. Applying that one, we will get the integral as number 3, taking minus 1 by a as common outside. Now differentiating again with respect to x, left one is y dash of x is equal to minus 1 by a. Then we have to differentiate the two integrals, integral from a to x and also from x to b. So here we have to apply the Leibniz rule we have already discussed for finding the derivative of integral. So by definition, it is we know that the Leibniz rule is d by dx of integral a of x, b of x, f of x theta d theta is equal to integral a of x, b of x, dou f by dou x into d theta plus f of x comma b of x into db by dx minus f of x comma a of x into a of x into dA by dx. So since the lower limit a is a constant, this third term will be 0. And using this formula we can write it as, and here in the integral this will be equal to integral a to x dou f by dou x. Here the function is v of x into u of theta phi theta, of which only v of x is the function containing x. So its derivative is v dash of x into u of theta phi theta dou f by dou x d theta. Now the second term is, instead of the theta, apply the upper limit. Upper limit is x. So this will be u of x, v of x, phi of x into dx by dx, that is 1. Then the third term will be 0 since dA by dx will be 0. And on the similar way, we can find the derivative of the second integral, integral a to x to b. In this one, the second term will be 0 since the derivative of b is a constant. So derivative of b with respect to x will be 0. And the third term will be u dash of x into v of x phi of x minus u of x in minus u of x into v of x phi of x. Now we can see that these two terms will get cancelled. Then the remaining integral will be minus 1 by a integral a to x v dash of x into u theta phi theta d theta plus x to b u dash of x into v of theta phi theta d theta, and name it as equation number 4. Now again differentiating, we will get, again by the Leibniz rule, we have in the first integral v dash of x, its derivative will be v double dash of x u theta phi theta d theta in plus v dash of x u of x phi of x minus 0 plus integral x to b u double dash of x v of theta phi theta d theta plus second term will be 0 and third term is minus u dash of x into v of x phi of x. Since in this term we can't cancel this two terms, or we can take the phi of x as common and take outside. So this will be u v dash minus u dash v term, and there will be minus 1 by a. So we can write y double dash of x as minus 1 by, we are taking the integral terms together and then the remaining term. So integral a to x, in the integral sign we will have the second derivative term v double dash of x u theta phi theta d theta plus integral x to b u double dash of x v theta phi theta d theta minus integral minus then we split the terms as these two terms. The remaining is this and this one. So minus 1 by a into u v dash minus u dash v whole into phi of x. Okay, and now we know what is this one. This is the Wronskian of the two non-trivial solutions u of x and v of x, and we know its value is given as by the Abel's identity. Its value is a by p of theta if the Wronskian is in the variable theta. Here the variable is x, w of x is here, so its value is a by p of x, where p is the leading coefficient, that means the function multiplied with the y double dash of x. So substituting that value, we have a and a get cancelled, then this will be minus phi of x by p of x. So this will be equation number 5. Now we need to show that Ly plus phi of x equal to 0, where Ly is p of x y double dash plus p dash x y dash x plus q into y of x. So first of all we substitute all these y dash and y double dash in this equation, and we will prove that Ly is equal to minus of phi of x. Then we have the corresponding the equivalent differential equation. So Ly of x is, first one is p of x into y double dash of x. Then this applying equation, substituting equation number 5. So it is minus 1 by a integral a to x v double dash of x u of theta phi theta d theta plus integral x to b u double dash of x v of theta phi theta d theta. Then the last term is minus phi of x by p of x. There it is, so we are multiplying this by p of x. So this will be my p of x, and p of x will get cancelled here. Plus then p of x into y double dash plus next term will be p dash of x, p dash of x into y dash of x. So substituting equation number 4 and multiplying this with the p dash of x, we have p dash of x into minus 1 by a integral a to x v dash u theta phi theta d theta plus integral x to b u dash of x v theta phi theta d theta plus the last term q of x into y of x minus 1 by a integral a to x u of theta v of theta phi theta d theta plus x to b u of x v of theta phi theta d theta. So now we have to combine the terms, the integrals in some special manner. That is, first we look at all the first integrals. That means integral a to x. Here we have minus p 1 by a into p of x into this integral. In the second term, in the first integral, we can see that integral a to x, it is u of theta phi theta d theta v double dash of x. So minus 1 by a p of x into v double dash of x into u theta phi theta d theta, and this term also contains u theta phi theta d theta, and in this integral also we have u theta phi theta d theta. So we can add all that integrals, and similarly when we consider integral x to b, we can add all that one also. Here it has v of theta phi theta d theta, v of theta phi theta d theta, and here also v of theta phi theta d theta. So we can combine all that integrals from x to b. So minus 1 by a, we can reduce it as minus 1 by a in integral a to x. What all have integral a to x? First one is p of x into v double dash of x, v double dash of x, p of x into v double dash of x, plus in this term it is p dash of x into v dash of x, plus in the third term, in the last summation, that is q of x into, so minus 1 by a we have already taken outside. So this will be q of x into v of x, u theta, phi theta, d theta. All these are common. Then in all other terms, in all the integrals, this is common, u theta, phi theta, d theta. In the same way, we can write integral x to b as p of x into v double dash of x plus p dash x into u dash x plus q of x into u of x all into v of theta phi theta d theta, which is common in all integrals from x to b, minus the last term which is in this, which is this one, that is minus phi of x. So it is now we look at the equations. P of x into v double dash plus p dash p dash v dash, this is v, sorry, this is not a v, this is u. This is u double dash of x p of x into u dash of x plus q of x into u of x. So this in this term in the bracket, this factor in the bracket is LV, and this is LU. So we can rewrite the integral as minus 1 by a integral a to x LV of x u theta phi theta d theta from a plus integral x to b LU of x v theta phi theta d theta minus phi of x. Now we have from the definition of the functions or Green's function, it is already known that u of x and v of x are the non-trivial solutions of the equation Ly equal to homogeneous equation Ly equal to 0. That means Lv of x equal to 0 when x is uh, less than theta, and LV equal to 0 when x is greater than theta, or LV equal to 0 when theta less than x and LU equal to 0 when theta greater than x. So theta less than x means its upper integral is x. So in this integral in this integral or in this interval a to x LV equal to 0, and in the interval from x to b LU equal to 0. So in a to x LV is 0 and x to b LU is 0. So and we already know that v does not satisfy the condition in a, and u does not satisfy the condition at b also. So we have both the integrals will vanish and the only term remaining on the right side is minus phi of x. So Ly of x is equal to minus phi of x, or Ly plus phi of x equal to 0. So from this it is clear that y in the equation 1 satisfies the equation number 2. And now the boundary conditions y of a. Y of a, when we substitute y of a in a instead of x, x as a, we have the first integral will get vanished, and y of a, the value will be minus 1 by a u of a into integral a to b v theta phi theta d theta, and y dash of a will be again applying the definition, taking the definition of y dash from equation number 4, I think 4. Yes, in this equation number 4, substitute instead of x, find y dash of a. Okay, so first integral will be from a to a, that is 0. Then second integral will be a to b u dash of a into integral a to b v of theta phi theta d theta. Okay, that is given as equation number 8 uy dash of a. Similarly, we can prove that the boundary conditions, or from these two equations, that is 7 and 6, 7 and 8, it follows that the function y defined by equation number 1 satisfies the same homogeneous conditions at x equal to a as the function of u. Similarly, we can show that y satisfies the homogeneous condition at x equal to b as a function of v. Now, conversely, the differential equation 2 together with the associated conditions imply equation number 1, so that the two formulations are equivalent. That we have the second part, that is that we have already proved by the construction of the Green's function, by the definition of the Green's function. So that equation, that is for the equation Ly plus phi of x equal to 0. If phi is a non-function, direct function of x alone, then the corresponding equation integral a to b g of x theta phi theta d theta will give a solution for the differential equation. Otherwise, this will be or that means if phi of x is an indirect function of x, that is function involving y also, then this one will be the corresponding integral equation. So from this it is clear that the two equations are equivalent. Now we discuss some notes. Suppose, we have now proved that for the equation Ly plus phi of x equal to 0 with some homogeneous boundary conditions, the corresponding integral equation is y equal to integral a to b g of x theta phi theta d theta, where g of x theta is the Green's function. uh, Green's function, which is obtained from the integral equation, the differential equation Ly equal to 0. So now we consider if phi of x equal to lambda r of x into y of x minus f of x. That means if phi of x is an indirect function of x, that means involving y. We may deduce the equivalence of the differential equation Ly plus phi of x. That means Ly plus lambda r of x y of x minus f of x equal to 0, or other words equal to f of x, with associated homogeneous boundary conditions on the interval integral a to b, and the Fredholm integral equation y of x equal to lambda integral a to b g of x theta. It is g of x theta phi theta d theta, and now it is phi is lambda into r of theta y theta d theta minus integral a to b g of x theta f theta d theta, where g is the Green's function. So this will be the corresponding integral equation. Also the solution of the problem, the y double dash equal to f of x, y of 0 equal to y of l equal to 0 is y of x is equal to minus integral 0 to l g of x theta f of theta d theta. This is because we have already proved that when the equation is in the form y double dash plus Ly plus phi of x equal to 0. If the equation is Ly plus phi of x equal to 0, then corresponding integral equation or the solution will be of the form integral a to b g of x theta phi theta d theta. Now here the equation is of the form y double dash plus f of x, f of y double dash minus f of x equal to 0. Therefore, the corresponding integral equation will be y of x, or solution, not the integral equation, since the function phi of x is minus phi of x minus f of x, which is a function of x alone. Therefore, its solution is given by using Green's function. Its solution is of the form integral. We have the lower limit and upper limit are 0 and L respectively. So 0 to L g of x theta into minus f of theta d theta. So it is minus integral 0 to L g of x theta, the Green's function, into f theta d theta. Thus we have the solution as in this form. Okay, let's stop here. Thank you. Thank you all.